Much, Nick. Right, it's actually very timely to be talking about outbursting comets, because in 2015 we've actually had 4 outbursts from 3 comets, and they actually all happened within the space of about 30 days. Now that's a real rarity. Outbursting comets, okay, you've heard about them, but what I'm talking about today is not fragmenting comets. I'm not talking about an outburst where a comet loses its integrity, it loses its strength, and it starts to break apart. Those events happen usually when a comet is approaching perihelion or just after perihelion, when it's most thermally stressed. What I'm talking about today is a much smaller group of comets which outburst, and after the outburst they just go on as if nothing had happened. And that's what happened with Comet Holmes, which Nick has already shown you. Was seen as a second magnitude star. It still is around, and it only lost about 2% of its mass. Now, how many outbursting comets are there? This is the list that I've put together. You can see Holmes there. About half of them are long period comets, and the ones that don't have periods are all within 5 to 8 years, so they're Jupiter family comets. And the one, here's the one down here which Nick also showed. That one has a 2,000-year period. So these number only about 4% of the total number of periodic comets known. So they're a rarity, there's something unusual happening. And these 3 are good examples of why we should be interested in them. All of these outbursts, you see the similarity between them in terms of their asymmetric appearance, but they happened at long distances, much further away from the sun than you would regard as perihelia. And so they're doing something which we, or science, is not able to explain at the moment. Okay? So you might be interested in outbursting comets near perihelion, but the ones that really are going to tell us something new are the ones that are misbehaving in a way that we can't explain. That's how science moves forward. You know, our theories and our understanding of Mother Nature and what there is out there is lacking because it can't explain why these comets will do this. And these are the sorts of magnitudes that you see for the major outbursts. And what's going on here? You know, how can you get so much energy released? One of the things that I think the literature has accepted is that there has to have been a build-up of pressure beneath the crust. These are comets that aren't like 67P's comet. 67P is likely to fragment at some time, and it might happen at this perihelion. And those 2 lobes that we saw on those very impressive pictures will break apart. What we're looking at here is repeat performances, and the 29P is the greatest actor in this respect. And I've put forward a hypothesis that the working hypothesis is that all of these objects must be slow rotators. They spin very slowly. And another one which will be more difficult to prove is that some of the ices are melting within the nucleus. Now, Comet Halley, here are some observations from Sir John Herschel back in 1836. And even Comet Halley did what a similar outburst as Comet Holmes, and that's Sekanina's. It's been reproduced here so that Holmes and Halley look rather similar. And here's a set of images that Dennis Brzezinski took of 2012 X1. And again, it's this characteristic expansion. I won't go into that now. I want to tell you and show you observations and some of the analysis rather than the interpretation. But you can analyze those images with a rotational filter, which will show you the fine structure within the coma that you can't pick out by eye simply. And this is X1 linear. You can see the similarity with 29P. Holmes is rather different again, but Holmes was a very big outburst. And here's some just other processed images, including one of Nick's there, showing those structures and how you get those spiral structures and that. And that's not because of the rotation of the nucleus. It's a little bit more subtle than that. And another one was Comet Valles. And again, you get this envelope like a jellyfish. And if you again analyze that, and this is a 40-minute exposure with a 2-meter telescope, you again see structure within there. And I was chatting with Jan Valles at a meeting, and I think I've sussed out why you get those spiral structures. Now, here's just a schematic of the solar system and the way in which it's arranged on a log scale. And comets generally live for billions of years out in the Kuiper belt. But the gravity of Neptune takes hold, and they start to be pulled in towards the sun. They first become under the control of Neptune, but they're then handed down in a gravitational sense by each of the giant planets. And what's interesting is that 29P has only come down to the orbit between Jupiter and Saturn, and it's trapped there. It's never been close to the sun, whereas 67P has been toasted to a crisp, really. And if we again look at these images, these are at 9 to 14 AU, and the temperatures we're looking at are around about 50 to 150 K. So, something's got to be happening, and it's not water ice that's involved. Here are the sets of images taken, sequential night images of the recent Comet Holmes outburst. And that proves that Holmes didn't just do a one-off. In fact, if you look through the literature and you see how many outbursts there have been, this is a tabulation. And in fact, there were 3 outbursts in the 19th century. Then there was a big gap. Then we had the very large outbursts. But there have been a number of other ones. And obviously, it's fundamental to that particular object. And this is the sort of thing you'll see if you look at it photometrically, or if you take an image. You see a sort of stellar nucleus appear, whereas before it was diffuse. But if you analyze that, you'll be able to see that it's the brightness is kicked. And again, another outburst. These are only a fraction of a magnitude, but they're distinctive. And an observer will pick it out from a well-processed comet image. But the one I really want to talk to you about in the 20 minutes I've got left is 29P, because this is the one that has the key to our understanding much more about what comets are. Because when they exist as a far from the sun, they're still at the point that they haven't been heated sufficiently, that they've lost their volatile reserve and the gases and so on. And Fred Whipple, who's the sort of the father of cometary astrometry, he actually produced his first paper in his first year at university, Berkeley in California, on Schwassmann-Wachmann. And one of his major works that he did latterly was a thorough analysis, which he published in 1980, about 29P. And he coined that term dirty snowball, which we now think is more an icy dirt ball. In fact, we now know from Rosetta that it's harder than an icy dirt ball. But this is what 29P looks like if you get a time where you image it on a particularly active time. What you've got here is, in fact, 2 outbursts that have happened about 2 weeks apart. So you can see the outer halo, and in the inset there you can see there's a gap missing. It's like a fan shape. And then the second one is inside here, and again it's that shape but directed in a different direction. And we can take images and we get this characteristic shape quite often. Now, here's something I want to complain about, and that is we've had 25 years of Hubble Space Telescope anniversary. It has only once ever been used to observe 29P, which is sacrilege, really, in my book. That's the bad news. The good news was when it was observed, it happened to have gone into outbursts, a really bright one, about 10 hours or 8 hours before the first images were taken. They used 2 orbits of Hubble, and so they've got 2 sets of observations about 20 hours apart. Now, the data has never been published. I've got a copy of the draft publication that was going to be published. Fortunately, it wasn't, because it wasn't saying the right things. They thought it was a continuous jet that was building up and building up and then dying down. But in fact, it's much more of an explosive event, because it turns out that Herman Meek, who's a keen amateur, had taken an image of that just about, 12 hours or so before, 10 hours before, and it was 4 or 5 magnitudes fainter. So what I did is I got the images from the Hubble Legacy archive and analysed those with that rotational filter to see what, and you stack the images so you increase the signal to noise, and that's a sort of interesting pattern that you can see. I haven't got time to go into that. What I'd now like to talk about is a similar very bright outburst that happened in 2010, February, and it really got me started on this particular comet. So I got 2 favourite comets in my life that I hold dear, and one is Holmes and the other is 29P. That's because it just happened the next day after the announcement that this outburst came on. I happened to have time on the 2-metre telescope, so we were able to get some observations right at the outset. This is data plotted from the Minor Planet Center archive, and what I've done is average the data points. And there were actually the major outbursts, and then were 2 other ones afterwards. And this is all part of the story. The fact that you get outbursts happening shortly after, a week or so after. Fred Whipple actually picked up on this in his 1980 paper. He said there seems to be like a 5-day period or so when you get a second outburst. It happens more often than it should. You know, okay, you get a random maybe first one, but the second one kicks in soon after. And he started to think it was a 5-day rotation period, but that's not the case. These are close-up images of 29P taken with the 2-metre on the next day after the outburst. And what I've lined up here is this is the first outburst, then another outburst took place. There's a star image, and you can see that the Coma is much bigger, and that was the second outburst, and then the third outburst here likewise. Now we took some images and we got schools involved. We got something like 18 schools and colleges during this period to take images. And lots of amateurs. David Strange, I'm not sure if he's here, he actually got some very useful data, and Nick House of Wiltshire Astronomical Society. And so we've got filtered images, and what you can do is you can start to play tricks in the different filters and see if there's a difference between one filtered image and another. So if you subtract one image from another, you start to see some detail. Now this is what happens if you look at what happened after 3 days. That's the process image to show the structure, what was actually the sort of concentrations of the outflows. And these are the 2 different colour difference images, and you can see detail in there. That means there's compositional differences close into the nucleus. Another set on February the 8th. That if you do the same, we've got 4 different filters there, and so we're able to see, and you can see how, you know, if you could show that in colour form, you'd see that there was a distinct change. And this is an evolving process. Over the first few days of the Coma's evolving. And then 2 of the observations were just a day or so after the outburst, the February the 3rd and the February the 16th. So if you look at those closely, you'll see in the different colour of V minus R, you'll see that the direction of the fan of material is redder than the opposing direction, both in the first outburst and in the last one. Right. What we do to analyse the images, Nick's touched on it, and what you do is you can measure the amount of light in an aperture, and then you can start increasing the aperture, make it bigger and bigger, and measure how much light there is. And that will give you a measurement within each annulus of what the surface brightness is. If you plot that for the first outburst, these are the first 3 epochs of observation. This is what you get. It's a little bit like Nick's image he showed. So you've got surface brightness. So a dark sky in the UK would be about mag 20 per square arc second. So we're going down there to, you know, almost a factor of 100 fainter than a really dark sky. This is the residual Coma from a previous outburst, which is still measurable there. And you see how the February the 3rd, you see how the Coma expands there. But another thing you can do with that when you measure those concentric apertures, it actually gives you the center of gravity or center of mass, or the light, the photocenter, in that each of those measurements will tell you where the center of the light is. And that's a very precise measurement. So you can actually follow what happens if you start increasing the measurement size as to where the center moves. Obviously, if there's been a fan-shaped structure going one direction, the center, the photocenter as I call it, should move. And if you plot that, say for the very first observations, what you get, these are two different filters, the movement is in that direction. So there we are, we start with a 1.7 arcsecond diameter aperture, and you go up, and you see it's all moving in one direction. That's because that was where the outburst was heading for. It then has pulled back because the outer regions of the coma are dominated by the previous outburst, so that heads off in another direction. Now, I've done that for each of the three outbursts. And when you plot each of the three ones, you get the coma going off in different directions. And this is, you know, these are 0.1 arcsecond. These are really small changes. So you're almost working at the milli-arcsecond. Now, if you do the same, do the same measurements 2 or 3 days later, by that time, the inner coma has expanded and it's lost the information, it's moved out. And all you get is that plot. They all land on more or less the origin. So it's a new technique for monitoring certainly 29P's outbursts in terms of characterizing. We can go back to old photos and analyze them to see which direction the outbursts were heading. Here's some detail of the second outburst event. Fascinating the symmetry you get, and you can measure the speeds of each and the direction. That's what I've done there. If you do that for different times in the past, this is 2010, 2011, different outbursts, you sometimes find somewhere the patterns are like fingerprints, and it looks so the same thing is reenacted. Something is happening in a repetitive sense. And these come out with sort of periods of 50 to 60 days. And this is an indication that there might be the same source on the surface, but there's more than one of them. If there was one sort of cryovolcano, we'd have solved the problem years ago. But what exists are several sources that seem to be long-lived, discrete sources. If you start to try to see the wood for the trees, is there any pattern in that? What you can do is just plot the time difference between outbursts. So you're not making any assumption about its rotation rate or whatever. Now, when I gave a short talk on the Sunday at the previous Winchester weekend, I'd analysed 37 outbursts. Since then, I've been working on it much more keenly, and I've identified times of 67 outbursts in total, and that's what I've plotted here. And I've plotted the times between consecutive outbursts, but also, if you imagine it, there's a good chance if there are several sources that there'll be another outburst in between the same source going off. So I also plotted the alternate outbursts. And you see a strange, you know, in the histogram, you would expect on average it would follow that sort of dashed line, but there are gaps at about 30 days and 90 days, and there seems to be this excess at around 60 days, which ties in with the fingerprint tests that we did. So this was the point I was at last December, and then I realized that I was looking at 12 years of data. Well, this thing goes around the sun every 15 years, and everything out there spins at a tilted axis, really, like the Earth at 23 degrees. So there are actually seasons on these comets, and the Rosetta comet will be no different. And this comet, therefore, has a season that lasts 4 years or so. So what I did was I split the data up into the 3 seasons that it covered. And the most recent season had 26 outbursts in it. That's the data for the activity during the 2010 Feb to September last year. And so then what you're looking to do is, what is the period of this? So what you do is you've got all these times accurate to a fraction of a day, and you start to say, is there a pattern there? So what you do is you work out for different periods whether there's clustering in the data. And lo and behold, I just couldn't, it's one of those eureka moments when, you're going through the data and suddenly you get a signal. And the signal is because at a peak of 57.5 days, there's coherence in the data. In other words, for 26 sort of seemingly random events, they're not random at all. They're actually, there's a repetition by some of them every 57.5. Now what's this other peak, you might ask? 67.8 days. Well, that turns out to effectively be the equivalent of the 57.5. It's the beat frequency on the synodic period for the comet. So that's the calculation, the 14.7 year period. If you feed in 67.8 as the beats and you make that equal the synodic period, what drops out is a figure of 57.8. So that number is equivalent to 57.8. So the whole data says that this object turns so that it's not the rotation period, it's the time when the sun reaches the same point in the sky if you were standing on the comet. It's very close to the rotation, this idea of rotation period. And so now what we can do is we can take a period of around 57.5 days and see if we can apply it to all the data. So what it's maybe not easy to see, but the season I just analysed is the top one there. So that's what happens if you plot the rotational phase at a period of that value. You get a dirty great gap because one side of the comet is inactive. The sources are on the other side. And if you look at the other seasons, you can see the clumping. In other words, there's a single source at some of these locations. There could be two sources close together, but there's certainly a small number. And these things have been lasting for years and years. Anyway, from coming back to observing, after last year's Winchester, I corresponded with a French amateur called Jean-François Soulier. Fortunately, I used to work in France, so I can correspond in French if I need to. And he uses a 0.4 meter, right? And he does absolute wonderful work with this 0.4 meter. It happens to be in Chile, at Alan Murray's setup at Space Obs. But he knows exactly what he's doing. And the two of us have been following 29P. I've been using the Las Cumbres Global Observatory Network. And his points are the green ones, and mine are the ones I've derived of the red ones. And this is actually the comet when it's quiescent. Its magnitude is 16 or 17. He's using a 0.4 meter, and we're getting this sort of photometry. And normally we would have thought this was just totally quiescent and not doing anything. There are actually two outbursts there. You can see in the data, especially that one. That one there, there's an anomalous brightening, which I think is just material falling back down under the gravity of the comet, and it never actually gets going. That's up until the end of August last year. The apparition finished in beginning of November, so we kept on, and what we saw was this. Massive outbursts, sudden outbursts. The end of the season that I was analysing was this one, and this effectively is the start of the new season. So for the next 3 or 4 years, we're into a different phase of this particular comet's behaviour. And the first two outbursts of 2015 are these. And interestingly, Kevin Hills, using remote telescope, managed to observe it when it was actually on a rise. Now, I've worked out it probably takes about 2 hours to go from quiescence to outburst. So very, very few out of something like 20,000 observations in the MPC database. There were only about half a dozen where they've caught it on the rise. So one of the challenges for observers is to do that, is to see if we can catch it on the rise more. And the next outburst, I'm going to stick my neck out and make a prediction. If this one, the source here is the most active one, that one actually is the same as the Hubble Space Telescope source, if you plot the period back in time. And it's responsible for certainly the most active outburst for the last 20 years. If it goes off its next rotation, it will go off between April the 20th and 26th. So there we go, something to look forward to. I'll finish now, but maybe on Sunday I'll talk about what's actually happening, because the interesting thing about the chemistry of it is that it's really, oh sorry, I'll do the, it's really like a bottle of champagne. The mechanism that's happening is that when I open this bottle of champagne, you have a process that goes on, which was you have a dissolved gas that becomes supersaturated in the liquid, and that as you release that cork, that pressure, the crust of the comet, as soon as the pressure drops, the gas will start coming out at a very high speed. And effectively, my hypothesis is that both carbon dioxide and carbon monoxide are both responsible for outbursts. The carbon monoxide ones from much further from the sun, and the carbon dioxide, like Holmes, much closer in. So I'll save this till a bit later. I've got another couple of slides for tomorrow, but I need to come tomorrow. Sorry, I need to acknowledge the help of people who contributed, and Dennis, John Drummond, Roger Dimmock, George Vassar, Kevin Hills, Nick Howes, Nick James, Michael Mattiazzo, Daryl Surgison, Jean-François Soulier, David Strange, Eric Watkins. They have all contributed observations of 29p and 17p. And it's all grist to the mill. It's all telling us something more that we didn't know before. Thanks.